Week's lab, we're going to do a separation process. This is often referred to as a qualitative analysis. It's qualitative in the sense that we will find out what we have present, but we won't find out how much of the things we have present. You have to use other techniques to quantify how much of each material may be present in a chemical reaction. So the first thing we're going to do is we're going to have a mixture. And in this mixture, it's often important to be able to separate the components of the mixture. There are several different tricks that chemists use to take a mixture and separate it into individual components. First of all, we probably should recognize why that would be important. When you're doing a particular chemical reaction, there are often other products as a result of that chemical reaction that are really not of interest, not economically viable or useful or particularly wanted around. So you have to be able to separate various components of the product mixture to get to the ones you want. Another important aspect of this would be in chemical disposal. Perhaps you have a mixture of components from various chemical processes, some of which are not harmful to the environment, others are. So it would be nice to be able to separate the harmful components from the ones that are benign to the environment so that you could then, with a clear conscience, dispose of the benign ones down the drain and maybe do special treatment to keep the harmful ones out of the environment. So it's very important to be able to separate components in chemistry. There's a wide variety of tricks that we use to separate components. We can do so by the temperature at which they boil or melt. We can do so by the difference in their density in what we would call precipitation. We can do some things electrically to separate them. We can do things that we call chromatographic processes by which we use differences in the solubility of the components to separate them. In today's lab, we're going to perform our separations generally by reactivity and precipitation. Okay, so let's take a look at maybe what we will do to pull those things off. Right to the chase, and let's just look at the procedure which we're going to perform today to carry out our separations. We are going to begin with an aqueous solution that contains 3 cations. Now, of course, it contains anions as well, but somehow the 3 cations of silver +1, lead +2, and copper +2 have been placed into this aqueous solution. So what we're going to do is we're going to dispense 25 drops of a solution that has these ions in it for sure, and we're going to label that tube with a P to indicate to us that it is our practice tube. Then we're going to get a second one of these tubes, these so-called centrifuge tubes, and into it we're going to take our laboratory unknown. There are, of course, several of them available. We will choose from one of the laboratory unknowns. We will place the same amount of material in this tube, and we will label it with a U standing for the unknown tube. So we have 2 centrifuge tubes which we will begin with, a known tube and an unknown tube, and we're going to perform the same series of experiments on each. So what the P tube is sort of acting as, it is acting as our standard. We will note what results we get from various chemical reactions on the standard, and then we will compare what the same appearance is to our unknown, and then in our unknown it will be able to tell us whether which of these ions may be present. Now again, in the unknown might have no ions, it might have 1 of these ions, it might have 2 of these ions, it might have all 3 of these ions. So your task is to, in your unknown, based on the series of tests that we perform, can you decide what of the 3 ions that you see present here, silver +1, lead plus 2 or copper plus 2, which of these three ions, if any of them, are present in your sample. And again, what you will do when you're done is you will report to your instructor which of these unknowns was present in the particular sample that we worked with. So here's a picture of two of these so-called centrifuge tubes that I am holding with test tube holders. And these are the tubes that we will do the analysis on. You note one is marked P, that's for the practice tube. One is marked U, that's the one that contains maybe the ions, maybe all the ions, maybe only some of the ions present. Another thing we should have mentioned, I should have mentioned on the previous slide, is the unique shape of these centrifuge tubes. They're not the typically shaped test tube that you may be a little more familiar with. These tubes are shaped in a particular fashion so that they fit properly in a device which we call a centrifuge. And we'll say a little bit more about the centrifuge when we carry out some of the procedures on subsequent slides. Okay, so our test tubes have ions in them, and remember, the practice tube has all three ions for sure. The U tube, or the unknown tube, may have three or has a number yet to be determined. But in any event, the series of experiments we're going to perform here below will separate the ions from each other and characterize the ions so that we know qualitatively that each of them is present. So the first series of reactions is designed to separate the copper cations from silver or lead cations. And how we do that is, in this instance, we add a few drops of 6 molar HCl. Now, in particular, the HCl contains the chloride anion. And it turns out that both silver and lead form chlorides that are highly insoluble. In actuality, what that means is that the solubility product, the equilibrium constant governing the reaction between the solid forms and dissolved dissociated forms of these chloride ionic compounds, this is a very small equilibrium constant, meaning only small, very, very, very small amounts of chloride anion can remain in solution when lead cation or silver cation are present. So the vast majority, almost all of every ion of lead and silver form a solid which is more dense than the aqueous medium around it, and it sort of rains down out of the liquid environment in which it is being formed. We call this gravitational pull of the denser material through the less dense material. We call it a precipitation. Just like rain is a precipitation of water through the less dense air medium. So I'm going to precipitate solid silver chloride and solid lead chloride out of the aqueous solution of lead cations and silver cations. On the other hand, copper is very soluble. In particular, copper chloride is very soluble. Copper 2 chloride, this is, in fact. And copper 2 chloride would, if you like, have a very large solubility product, or a very large number governing the equilibrium between Cu plus 1, Cu plus 2, and Cl minus, and the CuCl2 solid form. So being a number that is so large makes it possible that the copper cations will remain in solution, as well as the chloride anions would remain in solution. Now, at the bottom of the slide here, notice I show the three possible net ionic equations of the formation of lead chloride precipitate, the silver chloride precipitate, and if possible, the copper 2 chloride precipitate. Notice I do show a product formed for the addition of chloride for the lead cations or the silver cations, but I show a no reaction for the presence of the chloride anions with the copper plus 2 cations because no precipitate forms in that case. Here are the two centrifuge tubes, P and U, after the addition of the 6 molar HCl. Now what we note clearly is that each of them has formed a precipitate. But to be completely honest with you, we haven't solved our puzzle yet. Certainly this is true. We knew for a fact to start with that the practice tube had all the ions, so for sure the practice tube should have shown a precipitate. Well, we see that the unknown tube shows a precipitate too, but we are not really sure what that precipitate is. We know this for sure right at this juncture, that the unknown tube must have silver, lead, or both silver and lead, because precipitates of those materials should form. What we don't know is if it has all of one and all of the other, or a mixture of both. And what else we don't know is, was there copper present? Because the copper was soluble with the addition of chloride. So if copper cations are present, they're still in the liquid or supernatant above the precipitate. So we need to perform a qualitative analysis on this. What we have done for sure is separated the copper from the silver and lead. If copper is present, it will be present in the supernatant above the precipitate. We need a further test to verify whether or not copper is present. First thing we're going to do is make sure that we have completely separated the copper from the now solid lead and silver forms. To do this, we're going to use a device which chemists employ known as a centrifuge. A centrifuge is a spinning device which uses a centripetal force due to spinning objects that spinning objects experience, a centrifugal force actually, that they experience. And what we're going to do in spinning them is force the solid material, the more dense material, to gather with gravitational pull into the bottom of the beaker to ensure that, into the bottom of our centrifuge tube to ensure that it all gathers in that base. Now, one of the reasons that centrifuge tubes are pointed at the bottom is because oftentimes the amount of precipitate which forms is very small. So if the centrifuge, or if you use the rounded tube at the bottom, the tiny amount of precipitate that may form may not be easily discernible on a very wide-based bottom of a tube. So with a pointy tube, of course, the volume occupied by the precipitate will look more dramatic. So the pointy end of the tube is used to facilitate if only tiny amounts of precipitate is formed. It is still easy to recognize by a chemist doing a separation technique of this type that there certainly is some precipitate presented, being presented from the supernatant above. Okay, so when we put this into the centrifuge, it spins very, very rapidly. And what this can cause is an imbalance of angular momentum by the placement of one tube on one side of the centrifuge. Kind of like when you put wet towels into the washing machine and they all pile up on one side and you turn on the spin cycle, the washing machine might start wobbling very dramatically. Well, this same thing can occur if you have an imbalanced centrifuge. If you put a tube on one side and turn this on, this spins so dramatically that the angular momentum it generates makes a torque so that the device actually starts moving across the laboratory bench. So safe practice of using a centrifuge means to take a blank tube containing liquid that has no reaction in it, but has about the same mass as your experimental tube, and put it exactly in the opposite slots opposite your experimental tube. This balances the angular momentum of the spinning tubes, and then you will have no wobble in the tube. It's kind of like opening your washing machine, spreading the towels out evenly around in the tub, and then turning on the spin cycle, and now your washing machine kind of hums along nice and smoothly. So what we are going to do is we're going to ensure through centrifugation that we have completely separated our silver and lead in the solid form from the copper in the aqueous form. After completing the centrifugation, we're going to get a disposable pipette with a little tip. We're going to put the tip on top of it, and we're going to carefully pull the supernatant, or liquid often called the decantate. It goes by several names. We will pull that liquid into the disposable pipette and place the liquid portion into a separate test tube. So this takes a little bit of care. You can't get the pipette extremely close to the solid because it will begin to suck the solid up in there. So you have to be a little, exercise a little care. It's virtually impossible to get every drop of the liquid off of the precipitate. So what this means is in the end, we're going to have to wash our precipitate, because really the precipitate will be contaminated by a solution containing the copper +2 cations. So we're going to have a hard time getting every drop of it out. But if you're very careful, you should not pull any of the solid precipitate up with the aqueous remaining supernatant. So the supernatant should certainly have separation of the copper +2 from the silver cation or lead cation. So now what we're going to do with our supernatant is we're going to perform an experiment on it to verify whether or not it does contain copper +2. Because right now, just looking at it, it may be hard to tell if it does. Now, if there's sufficient copper +2, it might look that pretty blue that we saw when we made copper +2 sulfate solutions. Remember previously when we did our colorimetry experiments, we made copper +2 solutions and they formed a pretty blue color. It's possible that if there's sufficient copper +2 in the supernatant, that the solution might give you that pretty bright blue color. But it's also possible that if there's a very low concentration of it, just like in our colorimetry experiments, if the concentration is low enough, there's not enough orange light being absorbed by this sample, and we would have a hard time seeing with the naked eye the blue color that would qualitatively tell us that copper +2 is present. So what we're going to do is add another material which will complex a little more intensely with copper +2 than water is complexing with it, and it will give us a more intense color reading. If your test tube that has the supernatant that was decanted above the precipitate from the previous separation does have the bright blue color, remember, that's an indication of a so-called complexation between copper 2+ cations and water. But what we can do is enhance that, particularly for samples which have only a small smattering of copper +2, and therefore to the naked eye it's really hard to see the bright blue color. If you drip in some ammonia, instead of complexing with the water molecules, the copper +2 will complex with ammonia. And it turns out that copper ammonia complexes have a vividly deep blue color even when the concentration is low. So by adding a few drops of ammonia into the solution, we will form a different complexation between the copper cations in solution other than a water complexation. And this has a very distinct color display when you do so. Here I show pictures of the test tubes containing the supernatant from our separation of the copper from the lead and the silver. Into each of the tubes, the practice tube on the left, the unknown tube on the right, I added some 6 molar ammonia solution. From this information that you're gathering here, and remembering that the practice tube had definitely copper cations present, the unknown tube is what we're supposed to be determining. So I added the 6 molar NH3 into both of them, and this is how the color of those supernatants appear after that addition. From this information, you are to determine if your unknown sample contained copper cations. The next series of steps are designed to take the solid which we previously formed when we separated the copper loose, and in this solid we are supposed to now separate the silver chloride from the lead chloride that is present in this solid sample. Now the first set of steps is actually done in order to remove any contamination due to maybe the presence of the copper. Remember what I said is when you use your pipette here and you draw the liquid off the top, which contained the copper, it's virtually impossible to get all of that solution off of the precipitate. So there's some contaminate of copper present. So the first thing we're going to do is add some water to it and then break up the precipitate, stir it up, and then recentrifuge it again so that we're washing the precipitate and hopefully getting most of the copper that was residual on that precipitate up into the solution because of its its soluble nature with chloride present. So the copper, when we wash our precipitate, should be in the supernatant above that when we reprecipitate. Now, if you're trying to be really careful with what is going on, you should probably wash and centrifuge and wash and centrifuge several times to try to get all copper contaminant out of your precipitate. But okay, so let's say we washed this a few times, trying to get any copper contaminant out from the mixture of precipitates which contain certainly lead or certainly silver, but may contain both. And our goal is now to get the lead and silver apart from one another after we've gotten all the copper out of the way. To separate the silver from the lead, we're going to use another complexation trick. I'm going to add 8 drops of 1 molar sodium acetate to the precipitate, which should contain the mixture of silver chloride and lead chloride. Then I'm going to put some liquid in there, and I'm going to put it in the water bath and heat it a little bit. And what's going to happen then is I'm going to form a lead complex, a lead acetate complex. This lead acetate complex is soluble with chloride, whereas the silver chloride will remain insoluble. So again, lead acetate cation has a relatively high solubility product in the presence of chloride anion, whereas silver chloride has a very small solubility product, and silver chloride will remain as a solid precipitate, whereas lead acetate chloride will be dissolvable in water and remain in solution. So by doing a trick like this, what we have managed to be able to do is to separate the lead from the silver by putting the lead in the supernatant while the silver remains in the precipitate. So here's a picture of my two centrifuge tubes after I have added the sodium acetate into both. Again, on the left is my practice tube. On the right is my unknown, which I'm trying to determine which ions are present. So there is an indication of precipitate remaining, and that is giving me a clue as to what's going on for sure. But just because I see precipitate remaining does not tell me that lead was present in the initial sample. Because, well, one thing I might be able to note is there a change in the size in the amount of precipitate? That would be a good indicator for sure, but I would still like a definitive test to know certainly that lead has been dissolved out of the precipitate and is now present in the supernatant in the form of a lead acetate complexation. So we're going to perform a qualitative analysis experiment on the supernatant to determine if lead is present in that aqueous form. But certainly what we have accomplished now, we hope, is a separation of lead cation from silver cation. First thing I'm going to do is get another disposable pipette, and again I'm going to carefully decant or suck off the lead acetate containing aqueous phase medium from and separate it from the solid precipitate at the bottom. Now again, we have to be really careful when we do this. We don't want to get the pipette down closely to the precipitate because it will end up sucking some of that precipitate up into the liquid, and that will contaminate and remix, if you like, the lead and the silver. We're working under the assumption here that the lead and silver have been completely separated. The silver is in the solid precipitate. The lead is in the complex form in the aqueous medium above. So by using my pipette, I'm going to be able to draw the liquid containing the lead apart from the solid silver. To my decantate or supernatant, or whatever we want to call the liquid above the precipitate, I'm going to add 5 drops of 0.5 molar acetic acid. Then I'm going to follow that with 3 drops of potassium chromate. And when I do this, I should get a yellow precipitate that kind of really, if I centrifuge, I'd see a yellow precipitate at the bottom, but the entire solution should turn a vivid yellow because of the presence of that solid Pb lead chromate that is forming. So the solution should turn a bright yellow by addition of these two chemicals, and this is a qualitative analysis trick that will tell me for certain that I had present in the, prior to this, a clear colorless solution that might have had lead in. When I add these chemicals, I have certainly determined for sure that lead was present in that liquid. So here's what happened to both of my test tubes when I added the two chemicals into each. Now, all I will say to you is that one has a much more vivid color than the other. That's all that is implying, is that one might have had more lead in it than the other. But in any event, what you're supposed to be able to do is, from the results of this test, is you are supposed to be able to determine if there was any lead at all in your unknown. That's what you're supposed to be able to determine from this if there was a color change. What remains to be done is to verify if any precipitate that was formed from the lead and silver separation remember the lead was placed into the aqueous medium by complexation and separated from a solid precipitate below it. But now really all we need to do is to verify that that solid precipitate does contain silver. Now look, there's a pretty good chance that it does contain silver because that's the only thing that would have been left over. But just in case you didn't completely complex all the lead, and maybe that's just the remaining lead precipitate that would be present. So just to make sure that it is the case that it is silver present in that precipitate, what we're going to do is reprecipitate it with a different anion selective towards silver. So I'm going to take my solution I'm going to take my precipitate, that was left over from complexation of the lead and removing the lead. I decanted off the solution containing the lead. I have the remaining precipitate from that, and to that I'm going to add 6 molar ammonia, and then I'm going to break up the precipitate with a pipette, and I'm going to dissolve all the precipitate. So I'm going to take what was a solid and reconstitute it as an aqueous solution with the addition of ammonia that I do in this particular step. To this dissolved sample that I just added the ammonia to on the previous slide, I'm now going to add several drops of Ki solution. And Ki contains the iodide anion. Addition of the iodide anion will form an insoluble solid precipitate with silver. So the formation of a solid precipitate indicates that I have silver iodide, and the silver iodide is a sign, of course, that I had silver cation present in that solution to which I added the Ki. Here's what happened to my test tubes. One, of course, my practice test tube, the other my unknown test tube. What I did was I added some ammonia to the precipitate that was left over from the separation with the lead, dissolved it all, crunched it all up, got it all into solution. Then I added Ki into each test tube, and we see a resulting precipitate. You are supposed to use this information in order to determine whether or not your unknown sample contained silver cations. This is a flow chart showing the separation steps and the qualitative analysis reactions that we perform today to prove or disprove the presence of either copper cation, lead cation, and silver cation. We took solutions, one practice, one unknown, and to each we first added HCl. In the presence of HCl, silver chloride and lead chloride precipitates would be formed and sink to the bottom of the solution. However, copper chloride is soluble and will remain in solution. So what you have done by the addition of HCl to a solution containing all 3 cations would be separate the copper from the lead and the silver. To verify the presence of copper in the supernatant or liquid above the precipitates, we first decanted the liquid from the precipitate. Then we add ammonia to that liquid, and that ammonia complexes with copper and makes a vividly deep blue color. And if you see the appearance of this vividly deep blue color, even with small concentrations of copper, you will know that you have copper present in the mixture of your three cations. Okay, so then what we do is we turn to the left side of the branch. We take the precipitates of silver chloride and lead chloride, and we endeavor to separate them from each other. To do so, we add sodium acetate and put them in hot water. And what that does is that the lead forms a lead acetate complex, which turns out in the presence of chloride to be soluble. So that will dissolve into the supernatant, whereas the addition of the acetate has no effect on the silver present, so the silver chloride remains. So what we would do by adding those two materials is to separate the lead into the liquid or supernatant from the silver which remained in the precipitate. What we do then are a couple qualitative analysis steps to verify that what was in the supernatant was lead, because it's clear and colorless before you do the following steps, so you really aren't certain whether or not lead was in the supernatant. And also, if there is remaining precipitate, it could possibly be that you did not complex all the lead, and that remaining precipitate could in actual fact be lead and not really be silver at all. So what we do is first we take and separate the supernatant from the solid, and allegedly in the liquid above we would have the lead acetate complex. So to that we add some acetic acid and some potassium chromate, and it should form a very bright yellow precipitate from the originally colorless solution, and that would tell us that we had lead cations present. Then we take the precipitate, and to the precipitate we add some ammonia to dissolve it, and then to that dissolved solution that contains silver cations we add some potassium iodide, which should precipitate silver iodide. So if you see a precipitate at that point, it indicates that you had silver cations present as well. So this is our flow chart showing the procedures that we carried out today. Your lab report should include an indication of what ions were present in our unknown. So based on the pictures you see, you should be able to prepare a very simple lab report, and this very simple lab report is only going to indicate to me that you understand which ions we had present based on the qualitative analysis experiments that we performed on our unknown sample.